I'm really excited to give this talk. Dan and I were talking about what would be something to be relevant to folks, and something that I've wanted to kind of talk about are things that I have learned the hard way over my career. And one of the great things about being an engineer, being a technologist, is we're always learning. Learning is very much a part of the job. And you're probably excited to learn. You enjoy learning. We enjoy learning. We enjoy getting in to new technologies. And when you kind of like look back on your own education, that formal bit of your education is actually like the easiest part, right? Because it's really well structured. Like you've got a lecture, you've got a lab, you know exactly what you need to go do. The knock on it is it isn't always pragmatic. But when it's pragmatic, it's great because it's pragmatic and it's structured. It's terrific. And it feels at the time really arduous. And it feels at the time like, oh God, like it would be great to just kind of be let free. And then you get let free and you're like, oh my God, like what do I learn? Where do I go? How do I apply my own kind of structure? And you realize that was actually a really easy time to learn. Kind of the next easiest way to learn is when you get into the workforce, you're now on the job, and like most engineers, you're learning on the job. We're a computer company. We make a rack scale machine, which I have really come to appreciate how little I understand about how computers work. I keep thinking I understand. It's like, when am I going to know how computers work? And as it turns out, not today. Definitely wasn't yesterday. It's not today. It's probably not going to be tomorrow, because these things are extraordinarily complicated. And I do ask, we've got a double E team, and I'm like, where is the definitive book on the printed circuit board? The printed circuit board is so important to everything that we do. You all have printed circuit boards in your pocket. You've got it in your backpack. We've got it in the data center. It is what has affected modernity. And yet there is no real book on the printed circuit board, believe it or not. I mean, like a definitive history of the printed circuit board. I would love to be proven wrong on this, by the way, but everybody learns about PCBs on the job. If you're double E, and I'm sure there's a course out there somewhere that really goes into the nitty gritty details of a PCB. But if you're thinking to yourself, boy, I learned on the job, but I'm sure these double E's all got it in school. It's like, well, no, we're all kind of learning on the job. And we're all learning by actually making things. We're all learning by being in an organization that has figured a bunch of stuff out. And that's, by the way, that is the next easiest way to learn, is when you're in an organization or a group where you've got peers, more senior technologists, and they have already collectively, the hive mind has figured things out. And presumably when you came here, part of your rubric was, where am I going to learn? Where am I going to learn new things? What is a team I'm going to learn from? Which is a way of saying, I want to absorb what this team has already figured out, what this group has already figured out. And that's really important. And that ends up being really formative, especially for those of you that are early in your career. You'll look back at Rokt as like, wherever it takes you, it's like, this is where I came up. This is where I learned certain things. This is, the school of thought that I have. And you will see this from other engineers. Certainly, I was at Sun Microsystems for 14 years, which I have to point out is a computer company. It's been defunct for so long. My daughter, now 11, thought it was a brewery, very strangely. She's like, I thought Sun Microsystems was a brewery. I'm like, does that make any sense? She's like, I don't know. I guess it's not a brewery. You're obviously upset about it. Not a brewery. Like, not a brewery. Not a microbrew, a microsystem. Okay, again, it's a dated term. But I was at Sun for a long time, and Sun had a real effect on me. And I got to learn a bunch of things the easy way at Sun. So easy way to learn coming from our organization. And I learned a bunch of stuff the easy way. So I was in OS kernel development at Sun Microsystems, and there were a whole bunch of things that, when I look back on it, were actually the easy way of learning things. So part of the reason that I actually came to Sun way back in the day, I'll talk about this a little bit later, but Sun was the only company that actually believed in the primacy of the operating system. This was in the mid 90s, which now makes it sounds like a long time ago, because it was a long time ago. And every computer company had decided that Microsoft Windows was the future, not Linux. Linux was a hobby project out of Finland. It was Microsoft Windows that was going to be the future everywhere. And every computer company had decided that Windows was the future. The only exception to that was Sun. And that's why I went to Sun as a young engineer, was because I believed strongly in operating systems development. I was really excited about that. And there were a bunch of things that came as a result of that. So, when I first came to Sun, one of the senior engineers said, "You're a hacker. We're going to turn you into an engineer." And I remember being like, kind of annoyed at that. Like, screw you. I'm an engineer. I may just be, I'm just graduate, but I'm an engineer. But now in hindsight, he was right. He was right. I wasn't an engineer yet. And that was these kind of formative years at Sun, where I got to learn a lot. I learned the craft of writing C, which at the time, by the way, felt very dated. I was being told by folks that like, no, C is not the future. It's all going to be C++. It's going to be then later Java. No one does anything in C anymore. It turns out people did do things in C, and a lot of very important work was done in C since the mid 90s. And I learned a lot about the importance of enforced standards. Why do you have a standard formatting style, for example? I mean, there was a time. Now, thankfully, I know you guys do a lot of things in Go, and one of the things that Go does right is really standardized format. You can disagree with the style or agree with the style, but you know that you can go into somebody else's code and you can parse it. Like, that's why that's important. It's technically important that you have a unified style. And that was something that was a bit iconoclastic, honestly, in the mid 90s. This was not true of a lot of software engineering organizations. A lot of software engineering organizations is like, do whatever you want. Actually, a bunch of things I didn't put on here that I should have put on here. The importance of code review. Code review was, and actually, if you go to, there was a person I think is now becoming a little bit of a relic himself. Joel Spolsky was a kind of an outspoken figure in the late 90s, early 2000s. I can kind of see all the Gen Xers kind of nodding along, all the millennials and the Zoomers, like a little blank. I've got no idea what you're talking about. It's okay. But Joel Spolsky famously had a test of ways to assess your employer. Do you remember this? And they had the questions to ask your employer. And if you think to yourself, wow, software engineering is awful, and it's like it just has always been terrible, go back and read that test if you want to see what real terrible software engineering is like, because he has you ask questions like, is there a unified style? Is there source code management? And you may rightfully be like, what do you mean, is there source code management? Like, that's like, is there a computer? I mean, like, obviously there's source code management. It's like, au contraire, not obviously. And it's like, but what is the alternative to source code management? It's like delivering source code out of your home directory, which is what people were doing. That's right. Jupyter Notebooks. Exactly. That's right. Maybe the Jupyter Notebooks, sorry, that's a little too close to the bone. That may be the kind of the modern day equivalent. But as it turns out, like source code management, really important development, unified style, code review, really, really important. And these were things that were, again, iconoclastic in the late 90s, early 2000s. I got very lucky because I was in an environment that had those things. One way I got really lucky, and this is really just true happenstance, Sun actually was the wellspring of the bring over, modify, merge with respect to source code management. So it used to be that source code management, when you had a team that was sharing a source code repository, someone would lock a file to modify it, and then no one else would be able to modify that file. And you may be like, I'm not understanding this. While they are doing their development, they have the file locked. Yes. It's like, that seems like a terrible idea. It is. It's a terrible idea because for all of the reasons that you might think that's a terrible idea, it's a terrible idea. And a much better idea, actually, is you get an entire copy of the repository. You make whatever changes you need to make. You get that completely self-consistent. And then you merge in any conflicts you might have with that parent repository. And when the only delta between your repository and the parent is the work that you have done, you merge it. This didn't exist in 1996. When I entered the workforce. This actually only existed at Sun, in this product called Teamware. And Teamware had been developed earlier in the history of the kernel group, in part because they had a very bad a product that had good ideas but a very bad implementation. And the kernel group basically implemented their own thing. It was called NSE Lite by a guy named Larry McVoy. And so Larry had pioneered the bring over, modify, merge model. Larry then later left Sun, was at SGI, and had a company called BitKeeper. And BitKeeper was an available but not open source software product that allowed people to do the bring over, modify, merge model. And in particular, Larry McVoy did something that I didn't think was possible. He persuaded Linus Torvalds that he needed source code management. The Linux kernel did not have source code management all through the 90s and early 2000s. And as a point of principle, which makes absolutely no sense. And McVoy talked Linus into taking source code management in the form of BitKeeper. And then Larry got upset that someone was reverse engineering his proprietary software, which is very strange for someone who should have been a pioneer in open source. And there was a big kerfuffle. And Torvalds is like, I think I can do my own thing. And did his own thing called Git, which is what we use today. And it's pretty ironic that Git was developed by someone who was like morally opposed to source code management. But kudos to McVoy for getting Torvalds to kind of see the light in that regard. Kudos to Torvalds for developing the tool that he himself wanted. And in particular, Larry was developing source code management that he thought people would want, but he himself, what he was actually developing was BitKeeper. Torvalds was developing the kernel, so it was very important for him to have the source code management that he wanted, and that ended up being Git. So what you have today with respect to Git, I feel like I had in a time machine because I had it in the mid 90s, and it's great now that we all have this bring over, modify, merge model because it is the right model. Whether you use Mercurial or you use Git or you use something else, they all have. We're not suffering with perforce and so on, unless you are, in which case you know that you're suffering, and I'm not. There's no big news there. So I got very lucky in that regard. Another aspect that I got really lucky about was just the idea of rigorous first principles thinking when developing something. And this I've got to credit the engineer that I really came to Sun to work for, engineer named Jeff Bonwick, who developed the ZFS file system. I guess that's redundant. Developed ZFS, led the charge of ZFS along with Matt Ahrens. But Jeff is a singular engineer, and Jeff in particular very much believed in, I want to understand the problem that's being solved, and I want to solve it from first principles. And that was really inspiring for me to see. It was really inspiring for me to see and learn from an engineer that was like, no, I'm going to take this thing down to the studs, and I'm going to see what problem we are actually solving, and I'm going to solve that problem. And as a result, when he did that, he saw that there were a bunch of like other problems that were just kind of like secondary cruft because the actual primal problem had not been solved correctly. And this is first and foremost with respect to the memory allocator in the kernel. The kernel had a bunch of different memory allocators. They were all kind of junk. And Jeff rewrote the memory allocator. And when he rewrote the memory allocator, he took it down to first principles and developed something called the slab allocator that was then Linux and other basically every other operating system has the slab allocator or a variant thereof that Jeff developed. But he did a lot more than that. When you decide you're going to rewrite the memory allocator in an operating system, you can imagine that anything in that operating system that corrupts memory, because this is C, it's much easier to corrupt memory than it is in Go or Rust, certainly, other kind of dynamic or safe languages. And anything that corrupts memory will die where? In the allocator, right? Because when you corrupt memory, you are very likely to plow the allocator's state. And this is actually a really important lesson for me to kind of watch this, very important for Jeff, because Jeff had to exonerate himself all the time. And how do you exonerate yourself when everyone thinks that, like, hey, I ran it with the old allocator, it worked, and with the new allocator, I die. The kernel panics. It's like, yeah, that's because you've been corrupting memory the entire time, and you were actually getting away with it before. So Jeff added a really rich, still best of breed debugging facilities to the memory allocator so we could actually understand who was corrupting what, which we made terrific use of and used in lots of different ways. So that kind of rigorous first principles thinking was really inspiring to me, was really important to me. And one of the kind of very specific legacies that you can kind of see through the engineers that kind of came up this way is what Jeff called big theory statements, the large block comments that explain how a subsystem works, explains what you're doing. And I would really, really encourage you to write these kinds of comments. Comments are free, right? They're free with respect to the actual runtime, and they help convey your intent as an engineer. Here's what I am actually trying to solve. The minus with the challenge with comments, like all writing of your own ideas, it does require you to understand what you yourself are doing. And often you go, and this is why it's so important, right? You go to write that big block comment and you're like, wait a minute, why is this way? This doesn't make any sense. And you go to take it apart, you realize that like, actually, I've missed something here, right? You are the best reviewer of your own work. Nobody has the state that you have on what you're doing. And one of the things when I was talking to Dan earlier, I'm like, God, I got slides occurring to me that I should have made, but didn't, on learning things the hard way. But one of the things that I for sure learned the hard way is do not look to a code reviewer or an architectural reviewer to find things that you have missed. That can happen for sure. For sure that can happen. But the best reviewer of your work is you. And the best way for you to review your own work is to write down what you're doing, because that forces you to really think about it. And one of the things that actually we've done at Oxide in terms of our own engineering documentation process, and came out of learning things the hard way at Sun. So Sun, not unlike I think a lot of companies, had an architectural review board. Actually had many architectural review boards. You get these people that are kind of like to cosplay bureaucracy that get into a company. And they create this kind of like governance that just like flourishes, unfortunately. But there were all these architectural review boards. And when you were doing work, you would go to these architectural review boards. One of the things that we learned pretty early on was that the value in those architectural review boards was not actually in the board themselves. This group of chairs would have been much more effective as an architectural review board, because the chairs don't have any misunderstandings about what you're doing. But often the architectural review, because it's hard to get context on something that's complicated. And the value of those review boards was not in the people, it was in the materials that we prepared to go to those review boards. That was super valuable. And you go to prepare your materials and you realize like, wait a minute, missing some things here. I'm going to write my own documentation. Wait a minute, missing some things here. Write your own documentation. Another thing I've learned the hard way, another missing slide here, right? Write your own documentation. I think it's really, really important that you as an engineer write the documentation for your subsystem, because again, you will find things when you go to write the doc. Use your own APIs. Which sounds silly, but it's like when you actually use your own APIs, develop the consumer, you need to understand at any given layer of the stack. I don't care if you're at the bottom, the top, anywhere in between. You need to understand one layer above you and one layer below you. You need to understand how the layer below you works. You got to dig into that, wherever that is. If it's a database, if it's a web service, whatever it is, if it's the hardware, if it's the PCB, you're going to need to understand how that layer works, because if you don't, you'll abuse it, or when it misbehaves, you won't understand it. So you're going to need to understand how the layer below you works. Sorry. Hopefully you don't have to understand like too many layers below you, but sometimes things don't work very well. If they don't work very well, you got to understand a lot of layers. You also need to understand the layer above you. Who's consuming me and why? And the best way to do that is to be your own consumer, is to actually, and I'm sure many technologists have had this experience where I had come up with what I think is an awesome API, and I go to use it, and you're like, oh, actually, this may be an awesome API, but it's actually unusable. Because there is an important bit of state that is not conveyed in the API, or there's an implicit dependency here, or every consumer of this API is going to need to deal with some piece of trash, because I in the API won't actually deal with it. So it's so very important to be your own consumer, another kind of thing. Now, I think a lot of these things are things that I learned the easy way. Another thing I definitely learned the easy way at Sun, certainly, is the value of postmortem debugging. So postmortem debugging is debugging after the fact. So the bug happened. Is it reproducible? Is it not reproducible? We don't know, but the bug happened, and we have state. And that state, maybe it's a stack trace, maybe it is a bunch of log messages, maybe it's a core dump. And I'm a big believer that I wish that we had true post-mortem debugging across the entire industry, where we should be debugging from the actual in-memory state of these systems. So when your Go program dies, when it panics, you should, and you do get a core dump, or can get a core dump with Go, but then it's extremely hard to reason about your Go level state from that core dump. That's a travesty, honestly. And this is not a Go criticism. This is true for like most languages, absolutely true for Java. It's true-ish for Rust. But it's not necessarily true for C, where you can actually reason about what the in-memory state is from a core dump. So this is something that I got to learn the easy way. And then there's a whole bunch of things that I learned truly, truly the hard way. where it was not how I came up. It was like I literally did it wrong. And there's a bunch of stuff like this, as we were talking about earlier, the human side of engineering, which is really important, seems to have the most hard lessons. Not sure why. I got some ideas on why that is. I think that part of it is when, one of the beauty of you, when you as a software engineer, it's you and your code, right? I mean, this is where software engineering has got this unbelievable juxtaposition between this really like solitary time, right? Where I think every software engineer has introverted aspects to themselves, right? Where they actually like, no, I need some like quiet time with an editor. I just need to be by myself. And that is beautiful and solitary. The thing that's awkward is that we then collaborate. We have to collaborate. The software that we build is larger than ourselves. And so much of the software that we build is dependent upon that collaboration, that you're asking a bunch of people who have a predilection to introversion if they aren't absolute introverts. And by the way, this is true of me too. There are people who are like, oh my God, like what an extrovert you are. I'm like, definitely not. Definitely not. Like happy to speak to a room, also happy to be by myself with an editor, be by myself with a debugger. And thanks, like everybody get out, please. I'm gonna put my headphones on. I just want to be by myself. And I need that time. There are like people who are true extroverts, who I truly do not understand, who are like, I need people around me all the time. It's like, can't you just like calm down and like think on your own? It's like, nope, I absolutely can't. Thanks for asking. Let's go out, like let's do, and like good for those folks. They're not us. Yet we must collaborate. We have to collaborate with one another. And there's like this friction, this kind of friction that we have a hard time, and there are hard lessons in that friction. So I think that's why, but so we'll get to some of those. Let's talk about some of the lessons that I talked about a bunch of things I got to figure out the easy way. Let me tell you some embarrassing things that I had to learn the hard way. So post-mortem debugging seems a little esoteric. Learned that one the easy way. Testing doesn't seem esoteric. That one I did have to learn the hard way. Ironically, because an operating system kernel is actually really hard to test. An operating system kernel, if it is able to boot, it's a miracle. Like an operating system kernel that boots, you're like, hey, we're done. Which is like damn near the case, right? I mean, we once measured that we executed something like 38% of all code was executed upon boot. And then after having run every single test that we could run against the system, something like 40% of the code was executed, because so much code in the operating system kernel is really hard to test. It's around hardware that's misbehaving or things that don't happen. Very, very hard to kind of synthetically create these conditions. And unfortunately, it made me personally not really understand the power of testing, even when I was developing things that were much more testable. And so I was a late kind of convert on this. And I developed this body software called dtrace back in the day at Sun. And one of the mistakes we made is we didn't start the test suite early enough. We do have a test suite. And then we kind of like didn't really view writing those tests. And we viewed it as important, but we kind of like internally outsourced it. And the tests weren't very good. And bad tests are a problem, right? Just like you should write your own documentation, you as an engineer should write your own tests. And again, this may be one that I think more people broadly understand. This is where I had to learn some things the hard way, but that was definitely a hard one. Another thing that I certainly have learned the hard way, I feel like a couple of times over, and now have just got complete religion on it, is around building tooling. It's really, really important. Because I've seen so much of this happen around me, I participated in it myself. It is really important to build your own tooling. So the tooling is part of the magic of software, that we can build our own tooling. This is not in the physical world. It's harder to build your own tooling. It's a lot more expensive to build your own tooling. It's like we can do this stuff like pretty cheaply. Like in a weekend, you can do something amazing in software. This is becoming actually truer in mechanical and electrical engineering as you get more and more software influence in those domains. But historically, it really was not true. So we've got something really powerful that we can go develop our own tooling. We need to use this. And you should be developing your own tooling. The best person to develop the tooling is the person that needs it. If you need it, time to develop it. And so if you're like, well, someone else should develop it. Like, well, you need it. You know what's needed. You should develop it. And then I think it's a kind of incumbent upon leadership to support that, to say like, yes, this is important. And yeah, I know this is going to, and it's a challenge, right? Because when you have to stop and build tooling is not the artifact that we ship. The build system, the debugger, the editor, the linter, what have you. It's not the stuff we ship. The stuff we ship is the artifact. But the tooling is essential for that artifact. And if we constantly don't build that tooling, we have a system that we can no longer reason about. So it's really important. So how do you do that? Well, you can have dedicated tooling groups, but you got to be really careful. You end up with like Larry McVoy doing BK as opposed to Torvalds doing Git. You got to be really careful when you have a dedicated tooling group, because it's easy to lose the empathy for what actually is the important problem. So I would really encourage engineers, develop your own tooling. Build system broken, could be better, fix it. Unless it's Basil or Basel, how do we pronounce that monstrosity? Like that thing, push into the sea and do something else. But everything else, try to fix it. Sorry, we'll have to censor that out, or I'll get lit up by the internet when there's, actually I won't get lit up by the internet, and that's a sad thing. Basel maintainers, you know what I'm talking about. But you as the user of tooling, take responsibility, because again, you know what you need. The best time to develop a debugger is when debugging. And when you think about a debugger, you're like, all right, GDB. It's unfortunate that GDB is like our paragon of a debugger, because it's a trash pit of, it just is. I mean, it's just, it is something that is this kind of regrettable artifact that so many people have contributed to that nobody takes ownership of. And it gives you the idea that's what a debugger is. A debugger is something that stops the execution of my program and can single step it. That is fine. That is like one aspect of a debugger. A debugger is actually something that helps you comprehend your software system. That is what a debugger is. And hopefully to find defects. There's a lot of debugging infrastructure you can build for your software. And I would really encourage you to go build that tooling when you have a problem. Like when you have a problem and you know what we actually need here is like, we actually need to pull these logs into a system that is going to allow us to better analyze them. Like you're building a little bit of a debugger. You may have some other things do the heavy lifting for you, but you're building an apparatus that's going to allow you to understand software defects. And the time to do that is when you have a problem, especially one that you can't make forward progress on. All right, if you got a problem, you're like, I am stuck. You know what's great about a debugger? It's like pretty easy, relatively. It's like, yeah, okay, I can actually like, God, I got no idea what this problem is, but I know I could go like write some software to actually help me understand the software more generally. And in doing that, you often can generate you will understand your bug better. And if not, you've at least generated an artifact that is a debugger. I've done a bunch of debuggers over my career. I found it to be exceedingly important. And every single one of those has had relevance far beyond what I could have imagined. We actually done a lot of things at Oxide. We've got our own microcontroller on all of our servers and our switch. The traditional servers has something called the baseboard management controller, BMC. It's a monstrosity. It's not important right now. It's awful. And we have stripped that down to a microcontroller, and we've done our own operating system on that microcontroller, which seems crazy. We actually tried to evaluate every other operating system out there, but really wanted one that was de novo and Rust and a microkernel-based system, a bunch of things. So we named the operating system appropriately enough. We named it Hubris. And Hubris is open source. Go check out Hubris. Hubris is great. Love Hubris. I developed the debugger for Hubris, which of course is humility. And when we developed this, I was really just trying to aid my own comprehension of Hubris as we were developing it. But humility then has become the way we control everything with that microcontroller. And I never would have imagined this. We use humility on the manufacturing line to actually program the parts, to drop the software image onto the parts, to actually program them. Never would have imagined that we would have done that the debugging infrastructure would play that kind of outsized role. We don't ship humility. It's not part of the rack, but it's really essential for what we've done. So that debugging infrastructure can be really, really important. And the best time to do it is when you're actually debugging. Speaking of debugging, something that's very important in my own career, one of the things that I think is unfortunate that a lot of people need to learn the hard way is how to debug. This is not your fault. Education has failed you, has failed us, has failed me, has failed us all. If my life is long enough, I will write a book on this, I hope. on the methodology of debugging, because how do you debug? And there are people who are like, scientific method. I use the scientific method. And this is something that software engineers tell themselves because of our own inferiority complex. So, and I'm actually not sure to the degree to which this is true, but certainly when I was coming up, software engineering had a very deep inferiority complex. We are not real engineering. Real engineers build bridges. Real engineers build cars, build roads. We are not real engineers. So software has got a very deep inferiority complex. And so we try to make ourselves sound scientific whenever we can, just as like a desperate way of trying to up-level what we're doing. It's like, we use the scientific method. It's like, do you? Do we use the scientific method? Does science use the scientific method? I would argue no. The idea of the scientific method is like, we form a hypothesis. Then we conduct an experiment to attempt to contradict the hypothesis. Bullshit. You don't debug that way. I don't debug that way. First of all, I don't even like, I have actually debugged with what I would call euphemistically hypothesis-centric engineers. Drive me crazy, which is like, I know this, it's this. Boom, they're off. Like, I already made the change. It's like, wait, where are we right now? It's like, oh, it wasn't that. It's this. It's like, another change. Oh, no, it's not that. It's this. It's like, stop. Are you one of those extroverts? Stop. Settle down. Like, let's take a second. Let's like, a hypothesis is a guess. And let's not have guess-driven debugging, please. Let's have question-driven debugging. What question do you want to ask of the system? Imagine you had an oracle, lowercase o oracle, not oracle. Got a complicated, I worked for Oracle briefly, so I've got a complicated relationship with capital O oracle, little case o oracle. Imagine you had an oracle that could answer any question about the system. It's like, I want to know what the root cause of the bug. No, that's cheating. You can't do that one. Yeah, that's like wishing for more wishes. You can't do that. But the oracle will answer any other question you have about the system. What question do you want to ask? Then figure out, this is the question we would love to ask, even if you have no way of asking it. Then get creative about how you ask it. So many folks don't do this. They focus on either, I know this, guess-driven debugging, which is really infuriating because it often doesn't work very well, or they focus on the things that they know about. Like, these are the things we can know, so let's go look at this stuff. It's like, well, what are we looking for? What question are we trying to ask? So take a step back and ask, what question, if we had someone a genie who could answer any question, what question would we ask? Then take all your creativity and apply it to how you answer that question. Because you'd be amazed how often when you unlink these things and you come up with a really good question to ask. Now, as engineers, like, okay, wait a minute. No. I know a way we can go do that. I've got a way. I know, like, the existing system doesn't have the ability to do that, but it will leave these artifacts around that will allow us to go answer that question. So take a question-centric approach. And again, summon all that creativity to answer the question. When you have odd behavior in a system, another thing that I feel I've learned the hard way, you have something weird. It's like, that's not right. Why is that test suite like core dumping? That's strange. It's a Go program. Go programs don't core dump. They shouldn't. Okay, maybe if I just run it again. Oh, it didn't do it again. Okay, thank God. All right, it's not a problem. It's like, no. It's a problem. You know it's a problem, right? You know it's a problem. You can't unsee it. And it's very tempting to unsee it. And you can try to unsee it. And look, I've been there. I've tried to unsee problems. I mean, I still try to unsee problems because I don't want to have this stuff happen. Like, it's like when my teenager calls me, it's like, I know that's serious. He'll text me if it's good news, calls me if it's bad news. You can't unsee problems, right? So we had a bunch of computers, super micro-based machines, and we had 22 drives fail at once on a system. You're just like, what if I didn't come into work today? What if I didn't hear that? And I'm not here. But let's just play it out. Like, I'm on vacation today, but you're not on vacation, you're here. But what if I were on vacation? I would not know that this is happening. Therefore, it's not goodbye, right? No. 22 drives fail at once, 36 drives on the system really can't happen. They go to actually physically inspect the machine, and they're like, there's a dust throughout the system. It's like there's a Okay, now what's going on? It's like, now I really want to, okay, why is there a dust through the system? Obviously, a lot of follow-up questions there about, is there construction going on? Are we seeing this in other adjacent machines? And then as they're kind of like taking this machine apart, they're like, also, one of the fans is missing. Like, what do you mean missing? The blades were gone. And what had happened is the blades had disintegrated and blown through the chassis. And you're like, didn't see it. Like, maybe this will never happen again. And it happened to another system again. You're like, oh my God. So I definitely understand the desire to not see systems, not see problems, and not see odd behavior. But when you see odd behavior is odd for a reason. It's not what you expect. Your understanding of the system is wrong, or what has frequently been the case in my career, there's something deep in the system that's amiss. And we had exactly one of these. We had a cockroach test suite. Once every 100 times you ran it, the cockroach test suite would die. It's like, what is that? And then we use cockroach DB. Taking it apart, as it turns out, Go would die even when it's just kind of like initializing Go if you ran it once every kind of thousands of times. Turns out there was a rampant data corruption issue that Go is using some high performance registers that were not being initialized properly on us. And that was actually an arbitrary data corruption problem that was manifesting itself in this very strange, odd behavior that wasn't happening very frequently. And through that entire investigation, the engineer that was doing the investigation, which took actually months, the engineer's like, am I doing the right thing? Like, I'm worried that like we've got so much else to do. And I'm kind of like sitting here like why is there smoke coming out of this faucet? There should not be smoke coming out of the faucet. And it's like, yeah, no, we got all these other things going on. It's like, yeah, but why is there smoke coming out of the faucet? Like, no, seriously, why is there smoke coming out of the faucet? Turns out it's because the building's on fire. And glad that we debugged that, but it took a long time. It took a lot of resolve. So you want to understand odd behavior, really dig into odd behavior, and you will often find that even the worst case is like, oh, actually, this isn't odd behavior, and now understand the system better. And that enhanced understanding is really important. So another one that is actually has been really challenging for me personally. It took me kind of a long time to because I am a first principles engineer. I want to understand everything to absolute root cause. It's really frustrating when you can't do that, right? And what happens? So what happens if you can't debug it? Like, yeah, what happens if you can't debug it? Now, if a bug is reproducible, I don't care how psychotic it is, you can debug it. And if you need, I myself need this pep talk now, so I'm going to give you this pep talk that if you are because I cannot tell you how many times this has happened where I've got a bug that is no, but this bug is truly psychotic. I don't understand it. And I had that voice in the back of my head that said, if you can reproduce it, you can debug it. However psychotic it is, it may take you a while, but if you can reproduce it, you can debug it. You need that confidence. That confidence is really important because otherwise you'll be like, oh, I don't know, the system is magic, I don't understand it. It's like, no, understand it. If it's reproducible, you can debug it. It may take a while. You may have to grind on it. You can do it. Just like that cockroach problem. You can do it. It may take months, but you can do it. That's if it's reproducible. If it's not reproducible, you can also debug it. Way too many people give up on problems that are not reproducible. Oh, it's not reproducible. Like can we reproduce it? Oh, you can't reproduce it. And this is a huge anti-pattern in the industry. Reproduce it over here. Reproduce it on a Tuesday. Reproduce it without using vowels. Like this is all like these are just errands that we're sending ourselves on. When you have a problem that is not reproducible, you can debug it. You can debug it from the state it left behind. And if you've ever done this, to me, this is like the most gratifying feeling in software engineering is you've got something that's left behind a core dump or left behind log messages. Everyone else has given up on it, and you grind on it and grind on it and grind on it. And you're like, wait a minute. I see and you're asking questions, not of the problem, because the problem is long since passed. You're asking questions of the state of the system. And you're digging and digging. Maybe you're writing your own tooling to get there. And you discover the problem. You're like, wait a minute. If I'm right, and this is the problem, if I just hit this API endpoint, if I just run this program, boom, system fails in exactly the same way. That was, and that, like, if you're a baseball fan, that to me is the walk-off home run of software engineering. That's like keyboard flip, walk the bases, kind of strut in front of the pitcher, ball sails into the bay. What's up? That is the best feeling in software engineering. But it's hard. It's really hard. It feels great, but it's hard. What do you do for that problem that is psychotic, doesn't leave behind any state to really speak of, and is non-reproducible? Yeah, those suck. Really want to avoid those. I try to give them a stern talking to that, like, bug, you got a choice. You can be psychotic or you can be non-reproducible. You may not be both. So, like, make a choice. Put on your shoes so we can, you try to treat it like a 4-year-old. Like, we're all leaving, bug. Become reproducible. But no, bugs don't listen. Like 4-year-olds, bugs don't listen. So what do you do about those? And one of the things that has been hard for me as someone that does like to drive to root cause is to accept a kind of defeat in that I can't debug this right now. I don't have enough state. But it's not okay to walk away from the system. You've got to figure out, like, okay, I don't have enough state, but how can I modify the system such that if it happens again, I'll have more state? And I cannot tell you the number of times this has been absolutely critical. And sometimes adding half measures that don't make any sense. We had this happen recently at Oxide, where we've got a full rack. We've got the software. We do the hardware and the software. And we're installing the operating system image on all of these machines, all these sleds in the rack. And we would get the scariest bug that you can get in anything that you do: data corruption, random data corruption. All right. When I say data corruption, I want to be precise about that. Data corruption does not mean your data is unavailable. It does not mean that your data is gone. It means that you, like, go to cat Etsy password and you see, like, Etsy MOTD. You see, like, someone's web log is sitting in your database. Scary as hell. It's chilling. It, like, defies the physics of the problem. Like, what is this doing over here? It's like, yeah, welcome to data corruption. We had a problem with data corruption in the operating system image. Like, shit, could not reproduce it. And so the engineer added, fortunately, didn't pause to, like, take my measure of this, but added the ability to actually checksum everything as was going through the system. Felt like a little ridiculous because it didn't feel like the problem was in the software that was getting this image onto the disk. And all of a sudden we're seeing checksum failures everywhere. It's like, okay, wow, what is that? All of this, by the way, ended up being, AMD and I are still in a bit of a disagreement about whether this is a microprocessor defect or merely a misunderstanding between those who develop microprocessors and those who develop operating systems. But suffice it to say, we've got some differences of opinion about what the operating system is allowed to do with respect to speculative loading through a TLB entry. Super deep problem. But we were only able to debug it because we started taking half measures. So those half measures can be really, really essential, even though it can feel like a kind of defeat. In terms of making technology choices, and I feel I've done this the wrong way so many times. It's the biggest mistakes that I have made with respect to technology choices is when I haven't been very deliberate about a choice. When I'm just kind of like, I don't know, like, I'll just use, I mean, actually, this is embarrassing to say, but one of these was around, like, I just started using, like, a Perl goober for something. And all of a sudden the Perl just started, and Perl is like Sun Microsystems, not a brewery computer company, Perl programming language. Not sure if that's like a, Perl is kind of losing its, rightfully. Perl is a mess of a programming language. You shouldn't use it for anything today. But Perl, as Perl does, started to kind of metastasize. And the next thing you know, I had like 10,000 lines of Perl, which is, let's just say you never want to be in that situation. And it's because, like, I hadn't been like, well, let me, like, do a bake off and let me, like, choose Perl. I didn't choose Perl. I just kind of just stepped in it. And then it metastasized. So when I either step in it or when I use a technology because everybody is using it, and we did this we used Postgres. Like, we used Postgres for an object storage service that we were developing at a previous company. It's like, everybody uses Postgres. It turns out I'm not sure if everyone does use Postgres, because the problems that we saw with Postgres were like, does anyone else use Postgres? Like, we're seeing, and I think we probably still would have used Postgres, but I would have liked to have known about a lot of these pathologies before we set out. And we could have. So a bunch of this stuff was knowable. And a bunch of these, like, Postgres problems, and there's, like, other problems, like Erlang is the same way, where Erlang has this kind of, like, church of reliability. So if you are seeing a bug in an Erlang program, it is you, the sinner, that have said, like, it is not beam, the righteous beam only like is tautologically correct. And it takes you a while to realize, like, wait a minute, this system is like undebuggable because you've got this kind of church of tautological correctness. So and it can take you a while as a technologist to be like, no, I need to actually like take this apart and understand it. But when you make technology choices, be deliberate about how you do it. And when you look at it, don't just, because when you're trying to compare, like, oh, I'm trying to compare, a cockroach to timescale, or what have you. When you're trying to compare technologies that like don't line up exactly, it's like are not exactly comparable to one another. They're big systems. They've made different trade-offs over the years, and you can also overanalyze them, and you don't want to necessarily do that. What I would say is when you look at technologies, look at the values of the people that develop the technology. Why does this technology exist? Who did it? Tell me the history of this technology. What do its users believe? And is that what I believe? If you go to like the simplest one of these, OpenBSD. OpenBSD, we care about one thing and one thing only, security. That's it. That is the beginning and end of anything we care about, which is very clarifying. Because if you, as a user of the system, care about anything that's not security or anything that endangers security in any way, we, OpenBSD, not me personally, not an OpenBSD committer, but OpenBSD is not interested. That's clarifying, right? So there are lots of use cases where that makes sense. There are a lot of other use cases that demand, frankly, a little more modernity than OpenBSD offers, where you want to do something else. There's a reason that you don't deploy on OpenBSD, I don't think. And maybe you don't deploy around OpenBSD. That would be a gutsy decision. So when you're looking at these things, look at their values. So I was at a company called Joyent. Joyent was the company behind Node.js. And we did a ton of stuff in Node at Joyent. And it didn't work out really well. And I kind of thought, like McVoy, kind of bringing source code control to Torvalds, I thought I could bring a sense of robustness and resilience to JavaScript. You can't actually civilize JavaScript. That doesn't work that way. And what I learned in doing that was that the values that Node had for itself were not the values that we had for Node. And by the way, no one wants to tell you that, like, by the way, we don't care about reliability. No one's going to say that. Or we don't care about robustness. They actually make it worse. Like, no, we do care about reliability. It's like, we do care about debuggability. Okay, great. So futures are a mess, and we need to not have futures in the system because they're not debuggable. It's like, no, we have to have futures. It's like, okay, so you don't actually care about reliability, or debuggability. Or rather, that's just not the most important thing, which is fine. And actually, when in 2017, long after we broke up with Node.js, the organizer of Node Summit is like, hey, could you give a keynote talk on Node? I'm like, bad idea. I got like nothing nice to say, bad idea. He's like, oh, no, that'd be great. It's like, what's wrong with you? Why do you want me to give why? I'm not going to go to like my ex-girlfriend and explain like why we broke up. That seems cruel. And he's like, no, I think that'd be great. I'm like, okay. And I'm actually grateful for this, of him kind of pushing on me a bit. So I'm like, okay, how can I actually talk about this in a way that kind of drains it of some of the emotion? Because we were upset. We were upset that, and they were upset. People were upset. How can we drain it of the emotion and talk about what actually happened? And the way that I reflected on it, it really was a fracture in values. So I gave a talk called Software Platforms Reflection of Values. That was a really important talk. And I think that for me personally to give, because it allowed me to kind of process this stuff. And I would encourage you to really weigh values heavily when you're looking at a technology. One thing to just throw out there is that I've learned the hard way. Predictions reflect the present, not the future. So especially if you're early in your career, it is natural, I certainly did this, to kind of overweigh the prognostications of the grown-ups. Just be super, super careful about that, because people have been wrong a lot, and people don't reflect on their own predictions. And they're kind of confidently wrong, and then they just move on to the next prediction that they're confidently wrong about. Predictions are important. It's important to for us all to kind of model the future in our head, but just be careful, and be especially careful if somebody is predicting the future to you in a way that is like, well, I want to go work on this thing. You're telling me that this thing doesn't have a future, but I really like it. I want to go work over here. do not listen to the person that they're telling you. I so many times in my career, I've known people who in the 90s were told there's no future in software, and were computer scientists who went into the law and are miserable lawyers. Don't do this. If you're super Jones about the law, like definitely go be a lawyer, but like don't, like in terms of your own career path, chart it based on your own gut. Don't let people tell you what is and isn't going to happen, because they don't know. They don't know. It's real, as Yogi Berra said, it's really hard to make predictions, especially about the future. So just be cognizant of that. The way, by the way, this was internalized for me personally. We would get at the first of every year, we would get the engineers together back at Sun, and we would make 1, 3, and 6 year predictions. And then we would go back and look at our predictions, and oh Nelly, they are wrong. They are so wrong. And I mean, they're wrong in like every conceivable dimension. They're wrong because they're just like wrong. So that's like easy. They're wrong because of the stuff they missed. We were doing predictions from 2000 to 2007. Never predicted the rise of cloud computing. Ever. Didn't see it. Like a really important secular trend in my own career. Didn't really see it. But there's so many predictions we didn't make. So they're wrong by what they miss. They're wrong. They're also wrong when they're right. I had a prediction in 2003, a 3-year prediction, that Apple would introduce the next must-have gadget, that it would be a combination MP3 player, camera, and cell phone, and that they would call it the iPhone. That was in 2003. That's a banger of a prediction. I also thought it was going to be a flop. I thought it was going to be a disaster. It's like, oh, let me finish the sentence. It's also going to be a disaster. You're like, oh man, you were so right. And now you're so wrong. So wrong. So wrong. In fact, I feel really bad. Okay, as long as I'm kind of confessing things, my barber, when they introduced the iPhone, is like, I think I want to buy some Apple stock. I'm like, you should not do that. The iPhone is a disaster. He has kind of forgotten about this, and I don't want to bring it up because I'm a little bit worried that if I bring it up, he's like, oh, glad for you to finally bring it up. I've got a spreadsheet that I mean to show you. So here is me having bought like 2 shares of Apple stock in 2007, and like, you'd be cutting my hair, pal. So I'm so sorry. I'm so sorry. I no longer give advice on it. So even when we were right, we were wrong. Even when predictions are right, they're wrong. So be really, really, really careful about someone else's predictions, and don't get too caught up in your own. Like if you're doing something that excites you, do it. Find a way to do it. And don't worry, when I went into OS kernel development, everyone around me was telling me this is dead. Nobody does this. In 1996, I won the generational lottery, and I had people trying to talk me into ripping up the ticket. You kidding me? So don't listen to other people. Do what excites you. So now we get into a bit of the softer bit, and I am mindful of time, so but I want to kind of go on for probably another 10 or 15 minutes here. This one is super important. So if folks read The Soul of a New Machine by Tracy Kidder, this is good. I get to give you the gift of The Soul of a New Machine. So if you take one thing out of this talk, read this book. This is a very well-written book. Tracy Kidder is a terrific author. The book is not without flaws, but it won the Pulitzer in 1981. And it's about the development of a new machine at Data General. And if you think you don't know what Sun Microsystems is, you definitely don't know what Data General is. Data General is also a computer company, long out of business. To be worked at DG, all right. No, all right. Hey, listen, I love it. Yeah, so if you've worked at DG, you have read this. You for sure have read this. And the computer, it's interesting because the computer itself was forgettable, actually. The computer itself has had no long-term impact whatsoever. Wasn't terribly innovative, had a bunch. But what is interesting is the story behind it and the soul in the new machine that Kidder, and you will see something of yourself in the engineers that Kidder talks about, which is amazing. You think, again, this book, 40 plus years old, and the fact that it has any relevance today is shocking. It's a very good book. I found that it also rewards multiple reads. And when I read it as a young engineer, I read it, as a young computer science student, I thought it was amazing. But the things that I like really remembered are not what resonate with me as an older engineer. And I went back and actually reread it cover to cover a couple years ago. And there were all sorts of things in there about like, how did I miss this? Well, you missed it because you're 21 and you're a dumbass when you're 21. And you're just interested in other elements of it, interested in more technical elements of the story. But as I get older, I'm more interested in the human side of the story. And by the way, it's the soul of a new machine. It is the human side of the story. And in particular, and this was very iconoclastic at the time, Tom West, who's this engineering manager at DG, Tom West has this quote that this is like my one paragraph crash course on running or managing a team. That fall, West had put a new term in his vocabulary. It was trust. Trust is risk, and risk avoidance is the name of the game in business, West said once in praise of trust. He would bind his team with mutual trust, he had decided. When a person signed up to do a job for him, he would in turn trust that person to accomplish it. He wouldn't break it down into little pieces and make the task small, easy, and dull. Everything that, if you are a manager of a team or you're on a team, everything that you do should be to bind the team with mutual trust. Now, the highlights of my career have all been around a team bound by mutual trust. Because there's a bunch of like bullshit that you don't need when you're bound by mutual trust, actually. If you trust your colleagues to do the right thing, it's like all this kind of like OKRs and MBOs and perf reviews and all this other kind of bullshit. Like a bunch of that can fade away. Not to make it overly specific. Not to make it overly specific. Sorry. Right, exactly. And they're like, and this talk is over. All right, thank you, Bryan, for coming. It's like, hey, no, wait a minute. I've got a lot more things to say about perf reviews. Okay, so yeah, before they make me walk the plank. But I do think that trust is important. And what we do on our teams should be to enhance that trust. And when you trust your colleagues, that's when magic happens, is when you build that trust. So think to yourself, as you're doing things for the team, as you're doing, like, is this building trust? How can I build trust? What are the things that we can go do to build trust? So model yourself on West in at least that regard. The other thing I would say is kind of the flip side of this, which is around fear. So fear is a very base and important human emotion, right? Fear keeps us alive at some level. Fear prevents you from walking into the street or to walking into other pedestrians in New York. I love about New York. I feel like I could get killed by other pedestrians, which I actually just love. But that fear is important. But the fear is very base. It is a fight or flight reaction. Like there's no kind of like, think. It's all fight. Like that fight or flight reaction is very, very base. And I think a lot of conflict in the world generally, but certainly in an organization with teammates, has fear at its root. You're both afraid of something. And it can be really helpful. It can be like, hey, you know what? Like, we're both upset. I think we're both like, what are we afraid of? What are you afraid of? What am I afraid of? And not saying you shouldn't be afraid. I'm saying like, write it down. Like, here's what I'm afraid of. That's what you're afraid of. Like, like classic tension in engineering between rigor and urgency. And we are at loggerheads because you say, hey, we got to get this thing shipped. And I'm like, yeah, but we don't understand this odd behavior yet. Well, okay, well, what's our fear? Your fear, hey, we got a big deadline coming up. And it's like, if we don't get this thing out here, we're going to lose a major customer. And like, we got to actually like put dinner on the table. Someone's got to pay for the buffalo pizza around here. Okay, my fear is if we don't understand this odd behavior, it will manifest itself. Like, this is our last chance to understand this odd behavior. And it will be even worse for the customer. And it'll be a big blow up. And that doesn't necessarily resolve the conflict, but it allows you to get to like why you're both upset. Flip over the card. Why are you afraid? And you also may find that like, okay, wait a minute. I understand your fear. You understand my fear. Maybe we can more rapidly get to true consensus. For this, I would really, really strongly recommend Rachel Stevens gave a great talk at Monktoberfest. It's a Stevens with a, sorry, I should Stevens with an S there. That's a typo. But she gave a talk at Monktoberfest conference. It's online. You can find it, called Introspection Gaps. This is a must watch to understand, like, why do people behave badly? And so frequently it's fear. And if we can get curious about that fear, if we can summon our own curiosity, we can help on that conflict. So the last thing I've learned the hard way, again, there's a lot more that I've learned the hard way, but the last thing I'll kind of bore you with now, before I upset management any more than I already have. One thing that the biggest single mistakes that I have made in my entire career are mishires. And a mishire is not someone who just isn't productive. And it's actually not even necessarily someone who's an asshole, although that's obviously like not good. That's bad. When you have someone who doesn't have integrity, tells different people different things, is a political operator, is charismatic, you kind of add all that stuff up, that is the destroyer of organizations. Don't have any of those at Oxide, fortunately. Have had those in my career. It kills me to say this, but those folks have been necessary for me because it took one of those for me to really realize that everything I was doing around hiring was broken. And I hired someone who came in under an assumed name. As it turns out, I just got off parole for violent crimes. Talked more about that one over dinner. And that was actually not even the worst thing about him. Like also, there was also like lots of other problems. But there were others. This was the one that was non-negotiable, being like, you have hired the worst person in the world. I actually do love when I'm with especially other folks who have hired, when I say like, I've made the worst hire. They're like, well, actually, that's funny because I feel I've made the worst hire. I'm like, that's cool. But my hire, like assumed name, just got off of parole, violent crimes. Like, let's roll. Like yours is even worse than that. They're like, actually, you've made the worst hire. I'm like, okay, thank you. That's all right. Thank you. But it forced us as a team to strip it all to the studs. Everything about interviewing for me, the way I was interviewing, was busted. And we had to take a very fundamentally different approach. And I'm not saying this approach is for everybody, but the approach that one of the observations that we made is that if you really want to understand an engineer, especially an engineer, a technologist that's got that bias to being an introvert, an oral exam is the wrong way to do it. You actually want to evaluate engineers the way we do work on our own with the artifacts. Why do we have this oral exam to assess whether we hire someone or not? And what are we actually hiring for there? I mean, this was hit home to me. Actually, I should have learned this lesson the easy way much earlier in my career. The very first person whose hiring that I participated in was a person that I'd gone to school with that I desperately wanted to work at Sun. And let's go back. He'd stayed for his master's. I want him to work here. Really wanted to work with him. And he came and interviewed, and I was talking to the team and like, what'd you think? They're like, hey, I mean, I don't know. Like, I mean, like, you think so highly of him, but like, not that impressive. Like, what do you mean? Not that impressive? Like, this is like one of the best people I've ever worked with. And I'd gone to school with, we'd done everything together. What are you talking about? And what I realized was he was nervous as hell that entire day. He wanted to work with me and for Sun so badly and was so nervous that entire day and so guarded with his responses that people are just like, I don't know, I get like uptight vibes from this guy. It's like, yeah, he's uptight. He's scared as hell. Like an oral exam is the wrong way to assess him, actually. And it was funny because Jeff asked me, he's like, the thing I like to ask people is like, what would you do if we passed on this person? So what would you do if we passed on this person? I'm like, I would quit. I'd go work with him. He's like, okay, easy. I go, okay. I think that was not the answer he was expecting. He's like, okay, well, like we'll hire him. Like, be cool. We'll hire him. Had an unbelievable career at Sun. And I mean, it was one of those like, I should have realized at the time, like interviews don't work. Interviews don't work. At least the way they're traditionally done. I really encourage you to do as much as possible in writing in advance. And at the very least, so when we hire at Oxide, we've got a very writing intensive process. That's actually, effectively all of our evaluation is based on the materials that people submit, where we ask them questions like, I'm not interested in trivia questions or like inverting trees and all this other bullshit. I want to know, like, tell me some work you're proud of. Walk me through an analysis that you've done that you're proud of. Do you have any presentations that you're aware of? I want to see those. But I really want to know what makes you tick. When have you been happiest in your career and why? When have you been unhappiest and why? We are very explicit about our values. We've got 15 values at Oxide. Take one of our values and describe how it's been really reflected in your career. Take one of our values and describe how it's been violated in your career. How'd you deal with that? Take two of our values that came into conflict for you. How'd you resolve that conflict? Urgency and rigor are two of our values. So that's a very common, and as I tell people, like, there are no bonus points for being original, and urgency and rigor is like the classic tension in our domain. And I will never get sick of reading responses that talk about when urgency and rigor come into tension, because they come into tension every day for us. And then, and this is the bit that I think is replicable, is why do you want to work at Oxide? Just write that down. Like, why do we have people come in and spend 9 hours of their day, whatever it is, talking to a bunch of us without at least having like, why do you want to work here? Out of curiosity? It's like, oh, that's unreasonable to ask. It's really not unreasonable to ask, actually. And it allows people to like, I want to work here because, you know, I saw this YouTube video that you all did that I loved. That was awesome. And like I love the way that you encourage engineers to up-level themselves. Like, that's why I want to work here. It's like, that would be nice to know. As opposed to this kind of like throwaway question at the end of an oral exam. Like, why don't you have that in writing in advance? So not always replicable. That's what we have found. I would really encourage folks to use values as a lens of hiring and get out of trivia questions and get out from underneath oral exams. Because even when they work, they're working by accident. They're not actually working. And if you do it the wrong way, at some point, you'll learn it the hard way. So I really don't want you to learn it the hard way. And just to wrap up, can we make the easy way the hard way the easy way? Like, how do we not have to relearn this stuff? And fortunately, you know, we're in an era where people share information much more freely, which is great. I mean, you know, for all of the kind of the criticisms of like TikTok, you know, my kids learned to cook on TikTok. And which is nice as a parent. It's like, gives you kind of a complicated relationship with TikTok. You're like, wow, this is amazing. We're just like, oh, this is on TikTok. It's like, okay, I guess but you're still wasting time on your phone though, by the way. You're not getting, okay, now I'm actually confused. But we, you know, we share this kind of knowledge and accumulated wisdom. And we have found that social audio, we do a weekly Discord that we turn into a podcast we call Oxide and Friends. Would really encourage folks to check it out, because we've got a bunch of senior engineers like trading and junior folks and so on, talking about the various challenges that they have had. And one thing I've been struck by is the number of young technologists that have come up to me and have been really, really grateful for Oxide Friends. I'm like, now, why is that? And what I begin to realize is that what we have done is we have replicated what I always loved as an engineer, which is that lunch table or dinner table with the senior technologists, where you as a younger technologist are just kind of listening to people swap war stories, and you're accumulating that wisdom. And that's harder now today, but it's also easier with social audio. So would encourage you to check that out. If you start your own, definitely let me know so I can like and subscribe. I think we as a discipline need to do a lot more of this, so we can make sure that the people that come up behind you can learn more things the easy way and fewer the hard way. With that, thank you very much. A couple questions? Yeah, you bet.
All right. We'll spend a few minutes, maybe give folks a chance to ask Bryan some questions, just to get things started. I'll be the first one. Right? What were your OKRs for the last quarter, by the way? I'm just kidding. So maybe I'll start with a question. You talked about some trade-offs before. What's an example? Maybe give us an example of where you had to trade off rigor and velocity.
Where we had to, so I feel that happens all the time. And like, I feel like I mean, I'm obviously predisposed to come down to, I mean, rigor is super important, but it is easy to be overly rigorous. I mean, as a super concrete example, we don't prove our programs correct. We collectively, not just we at Oxide, like we have, I mean, there are formalisms where we like draw the line. And it's kind of interesting on some of those formalisms. I have kind of discarded a lot of formalisms And in doing that, have really kind of opted into urgency versus rigor. And I think I've erred a bit. And there's a bunch of those formalisms that are, I've kind of put all formalisms in the kind of like program proving pot. And there's a bunch of stuff that's actually interesting in testing that is being done. There are a bunch of other formalisms that I think that there's like, as much as possible, you don't want to be overly pat about like, I choose rigor or I choose urgency. You want to find ways to balance them. And you want to be, I think the most important thing on that trade-off is to be upfront about when you're making a trade-off. Because I think it's also about like, as an engineer, especially if you're going to choose urgency over rigor, like as an engineer, you want to heard that like, hey, I've been heard, that like, I get it. Like, yes, I understand. And we do need to make a commitment to understanding this, but we also need to ship this thing. And I also think that on that, for whatever it's worth, I think that transparency is, to me, extremely important. And I think that sometimes we think that like technologists can't hear like the tough truth about the business. And I find that the tough truth is actually like engineers love the truth. And can actually, it could be, you know, it's like, oh, sorry, the reason I need you to, like, I know I've asked you to work on this thing that wasn't on the roadmap. It's because we actually already promised it to this customer and like they haven't paid us yet. And they're not going to pay us until like we fix this. It's like from an engineer, like engineers like live to serve. They're like, okay, wow, okay, that's great. Like you've really helped folks, like that context. You're not just telling me to ignore this important bug that I'm working on. You're telling me like, we got to go get paid by this important customer because this is important deal. Like I need you over here. And I think that like that it goes to trust. It goes to allowing people to understand why this trade-off is being made. It's a little bit of a non-answer to the question, but oh yeah.
More questions? Pass the mic around. Yeah, I've got one. All right, here we go.
Ladder. Just one question about the debugging all the things. So probably some good team or good organization, they are intolerant to this thing. They can debug in probably 1 layer or 2 layer deep, figure out everything. Even when they are extremely exhausted already, they still do this. Probably some other team or organization, they doing pretty badly on this dimension. Like they align to deliver the magic feature, even all the other things, they probably just ignore or whatever. The question is, based on your understanding or experience, what are the key factors differentiate between the good teams and the bad teams?
From a debugging perspective in particular.
Yeah, it is because hiring the right person is the key, or have a very tough manager who is keep feedback, do this, not accept it, or culture, or company culture.
Okay, yeah. So
what is the
it's a
thing
great
make a
question.
difference?
And it is a bunch of things. I mean, I do feel that like, just like when you have someone who's got like a lot of health problems, or like a lot of things going wrong, and when you have someone who's really fit, there are a lot of things that have gone right. And I feel that there are a lot of things that kind of that need to go right. I will tell you that from a pure like culture perspective, I mean, one of the things that I have always sought out in a CEO in particular is, what is your ability to deal with bad news? And CEOs should be like, the best CEOs are very good at bad news. And the worst CEOs are so bad at bad news, nobody brings it to them. And if you got a CEO that nobody brings bad news to, next thing you know, you're SBF looking at a 40-year sentence. So I think creating a culture where we support bad news, and not that like, hey, good news, everybody, I've got some terrible news. It's like, you don't need to kind of go to that extreme. But when you want to have a culture which says when someone hits a problem, they are supported in understanding that. You also need to have a culture where someone is like, you may have a team that's like, it's a new team, we're coming together, we don't understand this technology. Also comfortable to say like, we don't know what we're doing. Like, we've got a failure over here. We could really use some help understanding this. Like, we just don't know what's going on. People are afraid of getting that like fear as a root of a lot of conflict. Like, well, what are you afraid of? Like, well, we're afraid that the rest of the company is going to realize we don't know what we're doing. It's like, okay, so let's say actually, if you're afraid that the rest of the company doesn't know what you're doing, the rest of the company probably already does know when you don't know what you're doing. So like, we can put that fear to rest. Everyone already does think you don't know what you're doing. Because by the way, you don't know what you're doing, which is fine. So let's figure out a way, because we weren't born knowing this stuff. You're trying to debug. You've got a database issue. You're trying to debug. We've got another team actually that was dealing with an Aurora problem 2 weeks ago, and we've got some technologies that can. I mean, one of the things you've got here as an asset, I feel, is you've got a bunch of different teams working on different things. That's a lot of versatility you can build into a team and help cross-pollinate that a little bit. Because you may have, earlier I said that if a problem is reproducible, you can debug it. That takes a certain kind of confidence in a technologist to know that. And not every technologist knows that or feels it. They may be like, no, I don't know how to debug this. I know it's reproducible, but I'm getting the SQL error that I don't know how to debug, or I'm getting this transient error that I don't know how to debug. Help me. And I think having a culture where you encourage people to help one another is also one that is conducive to kind of spreading that knowledge around with respect to debugging. But it's a bunch of factors. I also think it's helpful on an individual engineer's perspective. You really want to sow your own sense of curiosity. How does the system work? I want to understand how the system works. And I do feel like the more curious someone is, the more natural predilection that they have to being able to actually understand the root cause of bad behavior. The other thing I would say, I've got the, as an engineer at Oxide phrases it to me, he talks about his butt power. Butt power is his ability to sit in a chair and grind on a problem. Butt power is super, super useful. And I don't know how you select for butt power, but if you take butt power and combine it with curiosity, that's a pretty potent combo, because you then you don't have to add very much to that to get somebody who's really comfortable going deep onto problems. Is that fair?
Great, thanks.
Yeah.
Any more? Oh, here we go. We got folks on the phone as well. So just put your hand up on the phone or put a chat message in. We'll get to you.
You talked about how learning is important, something that we like. What is something you're excited to learn about that maybe you haven't gotten a chance to dig deep on yet?
Oh, that's a great question. That's a really good question. God, I feel there is so much that I still myself do not know. I'll tell you like a really concrete thing that I have. We've done our own PCBs. We've done our own server. We've done our own compute slide. And I've nibbled at the edges of that a lot. I know how to read a schematic. I've never actually done my own board. I would love to do that. Do my own layout. I think it would be, layout is so crazy, in terms of especially even on a simple board, it's pretty nuts. So I would love to I just find that the deeper I go in computing, the more the more magic there is. I mean, it's incredible how much there is and how deep it is. And I guess my entire career has kind of been percolating down a little bit. But I just find that there's a lot still to understand about this stuff that feels pretty basic. That's a terrific question. I mean, I've so much learning has kind of inflicted upon me at high velocity that, and it's more just that I don't actively fight back. I think that because I also feel so much, and I think this is true for all engineers. It's you're not always learning about the thing that you're what would you be delighted to learn about? You're just oh, now I'm learning why this part is a piece of garbage, or why this thing doesn't work, or this crate doesn't work. You're kind of learning at the tip of a bayonet a lot. And you just get accustomed to that, being exciting. So that's where I still think most of my education is going to come from. But yeah, that's a really good question.
Hey, can you give us one stock we shouldn't buy?
Oh yeah, right, exactly. And just go out and just back up the truck on that one.
Any questions remote? It looks like we have Hilltop hoods here as well. That's our Sydney office, by the way.
Hey, Sydney.
I don't know if we can get them on the full screen there, it looks like.
As I was telling Dan, we were married in Australia.
Yeah. Is that Eugene?
Nice, there's Sydney.
It's quite early for them.
That is. Hey, Sydney.
Any remote questions? So I guess I have a question for you. If there was one thing you would have done differently in the course of your career, a lesson that you learned the hard way? What would you have done differently?
And I'm going to assume that Apple stock, purchasing Apple stock
Yeah,
in 2007 is off the table.
Yeah.
That's interesting because I think there have been times in my career where I have thought to myself, well, I wouldn't have made this mistake. These hiring mistakes I made were grievous. They were bad. They did huge amounts of damage. And there would have been a time in my career, like not that long ago, if you'd asked me when starting Oxide, I'd be like, well, I would definitely not make that mistake again. And we've built this extraordinary team at Oxide. And one of the things I was reflecting on with another colleague, and he and I had worked at this previous gig and had this grievous mishires. Like, you know what? I realized like we needed those folks to get to where we are now. Like, whether I like it or not, that grievous mistake was actually, I 100% would be hiring people the same way I was. And Oxide wouldn't be where it is. It just wouldn't be. Because the team has been so important and the hiring process has been so important. So I really hesitate to go back. And because I do feel like I won the generational lottery ticket. I don't want to go back and start dorking with the past because I think so much of my present has relied on that. And I think, again, short of like, buying NVIDIA stock at the right time and Apple stock at the right time and so on. But I think like, even that, honestly, it's like it's how everyone should know some very wealthy, very miserable people in their lives. Just to help clarify that like money does not actually solve all problems. And so even buying the Apple stock, I probably would turn into an asshole. I probably would have started Oxide and be a real problem. So I'm kind of loath to go back and replay any of it. I would like to not make those same mistakes again. And I think that that's kind of more the way I think about it is like, let's not do that one again. And like, what do we need to go do to never do that one again? And I feel that that's true for a lot of stuff that I've done where I want to improve what I'm doing to not make the same mistake again. But I don't want to go back and take that mistake away because the reality is I needed it to learn.
Cool. Well, thanks so much, Bryan, for coming out.
Yeah.
Thanks, everybody, for joining us. Before we leave, can everyone just pitch in and help out to try to get these chairs back in the normal order? And thanks, everyone, for coming.